So this is my optimization project for Professor Charity Coombs. What is optimization? Optimization in calculus is the process through which one finds the maximum and minimum values with the given constraints using calculus. This process can be used to find maximum or minimum values for, say, time, profit, or cost. So some examples are maximum profit of a business, the cost of an enclosure, which we'll see through my example, and the most efficient or minimum time travel route. Some guidelines for optimization. Step 1 would be to draw a diagram which will represent given values and identify the constraints. Step 2 would be to identify the optimization equation and write it in terms of the variables from the constraints. And step 3 would be to use constraints to eliminate all but one independent variable. Step 4 is to write the optimization equation expressed with a single variable. And step 5 is to use the first derivative test to find the absolute max or min, and if necessary, to check the endpoints. So here's my example question. An equestrian is building an enclosure for his horse and has an area of 4,000 meters squared available. He looks to build this with the least amount of fences possible. What is the minimum perimeter that this rectangular enclosure can have to be within the constraints? So here's my diagram of my constraints. As you can see, the width is labeled as y, the length is labeled as x, and my area is 4,000 meters squared. So the enclosure has to have an area of that 4,000 meters squared, but the perimeter must be the lowest possible value while remaining to have the result of the area mentioned above, which would be 4,000 meters squared. So we'll be finding the derivative of the perimeter equation, which is 2x plus 2y. And our constraint is that the area, which equals 4,000, equals length times width, or x times y. So if we want to eliminate all but one independent variable, that means we'll have to do some substitution. So if we have 4,000 equals x times y, we divide by x on both sides, and we get rid of it on the right side of the equal sign, leaving us with 4,000 over x equals y. Then we're looking for the optimization equation in terms of one variable. So if y equals 4,000 over x and p equals 2x plus 2y, then p equals 2x plus 2 times 4,000 over x. To rearrange this without the fraction, this can become 2x plus 8,000x to the negative 1, as we're bringing up that exponent from the denominator. And this derived becomes 2 minus 8,000 x to the negative 2. And the reason it becomes a negative is because we're multiplying times negative 1, and then we're subtracting 1 from the exponent and making that the new exponent. So negative 1 minus 1 is negative 2. So this becomes 2 minus 8,000 over x squared. Or if we want to have it all in one fraction, it's 2x squared minus 8,000 over x squared. So then we run the first derivative test, and we have that p prime equals 2x squared minus 8,000 over x squared, and we then set this equation equal to 0 and solve. So x squared equals 0, then x equals 0, but that doesn't make sense for a perimeter. 2x squared minus 8,000 equals 0. We add the 8,000 over and divide by 2, which leaves us with the following: x squared equals 4,000, or x equals square root of 4,000. The final step would be to go back to our constraints and see that y equals 4,000 over x, and so y equals 4,000 over root 4,000, and since we have a radical, we have to multiply times root 4,000, but then both 4,000s in the numerator and the denominator cancel out, and we're left with root 4,000 just as our number. And surprisingly enough, this would mean that our enclosure is in the shape of a square. As a result, the final answer would be that p equals 2 times root 4,000 plus 2 times root 4,000, which equals 4 root 4,000. Thank you.